Hello everybody. In this lesson we are going to study about the similarities of triangles and some of the theorems that are involved in the similarity of triangles. Recall in the previous video and in the previous lessons we studied about similar figures. So in this lesson we will study about the similarities of triangles. So welcome to the lesson. When do you say that two polygons are similar? We have studied that two polygons are similar if the corresponding angles are equal and the corresponding sides are in proportion. Now the question is, are the triangles also polygons? They are. So the similarity conditions will hold good for triangles too. So two triangles are similar if their corresponding angles are equal. That means if angle A is equal to angle D, angle B equal to angle E, and angle C equal to angle F, and their corresponding sides are in the same ratio. AC over DF is equal to AB over DE equal to BC over EF. That will be the ratio of the corresponding sides. So these are the two conditions. The ratio of the corresponding sides are in proportion and the corresponding angles are equal. So the two triangles are said to be similar if these two conditions are met. When the corresponding angles of the two triangles are equal, such triangles are called equiangular triangles. So what are equiangular triangles? They are those triangles where the corresponding angles are equal. For example, angle A is equal to angle D, angle B equal to angle E, and angle C equal to angle F. Then we say that these two triangles are equiangular. Remember this definition. So in equiangular triangles, the ratio of any two corresponding sides in two equiangular triangles is always the same. Now this is a rule. In equiangular triangles, the ratio of the corresponding sides will always be the same, and this is known as the basic proportionality theorem, or it is also called as Thales theorem. Now let us try to understand some theorems on similarity triangles and let's see how to prove them. Let's try to understand this theorem. If a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, the other two sides are divided in the same ratio. So let's represent this whole theorem diagrammatically. So let's draw a diagram first. Let's draw a triangle. Let's build step by step. So this is a triangle. Let us label that as ABC. Now let us draw a line parallel to BC, intersecting AB and AC. So we have drawn a line DE parallel to BC, intersecting AB and DE. Let us join BE and CD. So we have joined BE and CD. Now let us draw two perpendicular lines for the triangle ADE. So we have DM perpendicular to AE and EN, let's label that as N, perpendicular to AD. Now we have the whole figure. ABC is a triangle, DE is a line drawn parallel to BC, and DM and EN are two perpendicular lines, and we have joined BE and CD. According to the theorem, if a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, the other two sides are divided in the same ratio. It means that AD over DB is equal to AE over EC. That's what it says. It means that AD over DB is equal to AE over EC. This is the theorem 6.1. Can we prove it? Of course we can. And let's see how we go about proving this theorem. So we need to prove that AD over DB is equal to AE over EC. Now in the triangle ADE, what is the area of the triangle ADE? It's half base times height. Half times, if we take AD as the base, then what will be the height? EN will be the height. So area of the triangle ADE will be half base, which is AD, times height, which is EN. Remember that instead of writing area of triangle ADE, we can straight represent the area as AR. So area of triangle ADE is half AD times EN. Now let's move further. What will be the area of the triangle BDE? It will be half base, which is BD, times the height, which is EN. So for the triangle BDE, the area of the triangle BDE will be half base, which is DB, times EN. Now coming to the triangle ADE again. If I take AE as the base, what will be the height? DM. So area of the triangle ADE once again can be half AE, we are taking AE as the base now, times DM. Similarly, what will be the area of the triangle DEC, this triangle? The base is going to be EC and the height is going to be DM. So area of the triangle DEC is going to be half EC times DM. So we have figured out what are the areas of ADE, BDE, DEC. So what will be the area of the triangle ADE over BDE? We know that ADE is half AD times EN and the area of BDE is half DB times EN, and EN cancels, half cancels, so we will have AD over DB. Let's label this as equation 1. Now what will be the area of ADE over DEC? We know that area of ADE is also half AE times DM and the area of DEC is half EC times DM. So half cancels and DM cancels and we have AE over EC. Let's label this as equation 2. Do you observe that in the triangle BDE, this triangle, and DEC, these two triangles, BDE and DEC, they have the same base DE. They are resting on the same base DE. And between the same parallels DE and BC. So if two triangles have the same base and between the same parallels, we have studied in our lower grades that the areas of these two triangles will be equal. So the area of triangle BDE is equal to area of triangle DEC. Why? Because these two triangles have the same base DE and are between the same parallels DE and BC. So let's label this equation as 3. So, from equation 3, we know that area of BDE is same as area of DEC. So, instead of DEC, can I write area BDE in equation 2? I can. So, we can conclude that area of ADE over BDE, these two will become same, because when DEC is replaced by BDE, these two 1 and 2 will become the same. So, we can say that area of ADE over BDE, AD over DB is equal to AE over EC. Hence, we would have proved the theorem. So, from equation 1, equation 2 and equation 3, we can say that AD over DB is equal to AE over EC. AD over DB is equal to AE over EC. So, remember now, in any triangle, if a line is drawn parallel to one side of the triangle, intersecting at two distinct points D and E, then AD over DB will be equal to AE over EC. So, we have proved the theorem. Great going. This is a step-by-step proving of the theorem. What about the converse of this theorem? Suppose if I say that in this triangle ABC, AD over DB is equal to AE over EC. What can you conclude about the line segments DE and BC? What can you say about DE and BC? Because AD over DB is equal to AE over EC, we can say that DE is parallel to BC. So, that is the converse. DE will be parallel to BC. So, if you want to state this converse mathematically, this is how you can do. The converse of this theorem can be stated formally as, if a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. So, we know the theorem and we know the converse of it. Let's try this problem. If DE is parallel to BC, find EC. Let us label EC as X. We know that according to the theorem, if DE is parallel to BC, then 1.5 over 3 is going to be equal to 1 over X. And now cross multiply, X times 1.5 is equal to 3. X will be equal to 3 over 1.5, and that's going to be equal to X, which is equal to 2, which is nothing but EC. So, EC is 2 centimeters. So, we can apply the theorem to find the missing values for such conditions in the triangles. Let's try this problem. E and F are points on the sides PQ and PR respectively of a triangle PQR. For each of the following cases, state whether EF is parallel to QR. Let us first draw the triangle PQR and EF, and then we will label all the parts and then see what we have to do next. Now, for EF to be parallel to QR, according to the theorem, PE over EQ should be equal to PF over FR. Let's figure that out. PE is PE over EQ. So, PE over EQ, and PE is 3.9 and EQ is 3. And if we simplify that, it's going to give us 1.3 over 1. Now, let's figure out what's PF over FR. PF over FR. PF is 3.6 over FR is 2.4. Simplify that, we get 1.5 over 1, and these two are not equal. And since PE over EQ is not equal to PF over FR, we say that EF is not parallel to QR. So EF is not parallel to QR. EF is not parallel to QR. That is how we apply the theorem. Let's try this. Same one. We have to prove that EF is parallel to QR. Now given PE is 0.18 and PQ, the whole length, is 1.28. So how will we find EQ? We can easily find EQ by 1.28 minus 0.18, which will give us 1.1. Similarly, how can we find FR? We know the whole length PR, which is 2.56, and PF is 0.36. So 2.56 minus 0.36 will give us 2.2. So now we can apply the theorem. So let us check PE over EQ. What is the ratio we get? PE over EQ. PE is 0.18 and EQ is 1.1, and that's going to be 9 over 55. Now we will check what is PF over FR. PF over FR. PF is 0.36 over FR is 2.2. Simplify, you get 9 over 55. So the ratios are same. Therefore, EF is parallel to QR. Great. That's how we use the theorem again. Let's try this. ABCD is a trapezium with AB parallel to DC. E and F are points on non-parallel sides of AD and BC, respectively, such that EF is parallel to AB. Show that AE over ED is equal to BF over FC. Now, in order to do that, let's join AC with a straight line, and our figure will be this. And then let's go on to prove AE over ED is equal to BF over FC. So let's look at the solution now. AB is parallel to DC and EF is parallel to AB. That's given in the question. So what can we say if AB is parallel to DC and EF is parallel to AB? Can I say that EF is parallel to DC? Because lines parallel to the same line are parallel to each other. So EF is parallel to DC. So let's look at the triangle ADC now. So in triangle ADC, we have EG parallel to DC. Why? Because EF is parallel to DC. So EG will be parallel to DC. So can we apply theorem 6.1 and say that AE over ED is equal to AG over GC according to the theorem of proportionality? Yes, we can. Now let's move further. So similarly, if we consider triangle CAB, now if we consider triangle CAB, can I say CG over AG is equal to CF over BF according to theorem 6.1. So if I just take the reciprocal of that, I just reverse AG over here and CG down, flip the fractions. So what happens? Can I say AG over GC? It's the same thing, we are just flipping the fractions over here, is equal to BF over FC. Let's label this as equation 2. So equation 1, AE over AD is equal to AG over GC. Equation 2, AG over GC is equal to BF over FC. So what can we say? Therefore, from 1 and 2, can I say AE over ED is equal to BF over FC? Because AG over GC is this, AG over GC is this. So these two will be equal. So hence we have proved the question. Great going, good job. You can prove these type of problems step by step. Keep working, keep practicing. Let's try another one. Let's look at this. In the figure, PS over SQ is equal to PT over TR, and angle PST is equal to PRQ. Prove that triangle PQR is an isosceles triangle. First of all, what is an isosceles triangle? A triangle in which two sides are equal. So we have to prove that PQ is equal to PR. And if you are able to prove that, then PQR is an isosceles triangle. So let's look at the solution now. What is given? It is given in the question that PS over SQ is equal to PT over TR. So if that is the case, what do you conclude about the line ST and QR? Can I say ST is parallel to QR according to theorem 6.1? Yes. So it is given that PS over SQ is equal to PT over TR. So in that case, we can easily conclude that ST is parallel to QR. If ST is parallel to QR, this angle and this angle, what are they? We have learnt it in lower grades. If these two lines are parallel and if SQ happens to be a transversal, so can you guess what is this angle and this angle called? They are called corresponding angles. And when two lines are parallel, corresponding angles are equal. So can I say that angle PST is equal to angle PQR? Why? Because they are corresponding angles. So we know that angle PST is also equal to angle PRQ as it is given in the question. So PST is equal to PRQ. Let's label that as equation 2. Now, this angle is equal to this angle. This angle is equal to this angle. We have proved it in equation 1. So can I say that this angle is equal to this angle? I can. So angle PRQ is equal to angle PQR. These two angles are equal. Now, if the two angles of a triangle are equal, the sides opposite to them are also equal. So PQ will be equal to PR. So PQ will be equal to PR because sides opposite to the equal angles will be equal. So what do you conclude from this now? So from 1 and 2 we can say that since PQ is equal to PR, triangle PQR is an isosceles triangle. So we can say that triangle PQR is an isosceles triangle. Excellent. We have completed the lesson on similarities of triangles, but this is not sufficient for you all. You need to practice it. These are the concepts that are presented with some of the examples. Put in efforts because efforts produce results. So keep practicing, keep working on more and more problems. You will become proficient in this concept. Good going. Thank you for watching. Please subscribe and share with your friends and teachers. Thank you.